G'day everyone, and welcome to our lesson on magnetic flux, in which we're going to do practice questions to do with magnetic flux. The first question we're going to do is a question in which the area is a mystery and we're going to find it. They tell us that the flux through a loop that is at vertical, so the orientation which collects the most number of magnetic field lines and therefore the most flux, the flux comes to 4 times 10 to the negative 3. And they also tell us that the strength of the magnetic field between these two poles here is equal to 1.5 times 10 to the negative 3. And the one added complication is that there are actually 60 loops in here, all tracing the same path. So the area between inside each of these loops is equal to some mystery. And the number we usually give by n equals 60. What is the area of a single loop in here? Well, surprisingly, the flux does not depend on the number of loops in there. The flux is a measure of the number of magnetic field lines passing through a certain region of space. So we can work out the area just by using this simple formula up here. Flux, 4 times 10 to the negative 3, is equal to magnetic field strength, that's in Teslas, 1.5 times 10 to the negative 3, so I should put in units. Flux is in Webers, magnetic field strength is in Teslas, area is in meters squared, multiplied by the area. So I can get area by itself by dividing both sides by 1.5 times 10 to the negative 3. And I have that coming to 2.67 meters squared. I said that the loop, in this case, was in the orientation which allowed it to capture the most number of magnetic field lines. That is the orientation in which the area, which you can think of as, in that case, a square plate, it was standing vertically. The area, this plane here, was perpendicular to the magnetic field lines. If I had that loop, that coil of 60 loops in another orientation, this orientation here, so that it's now parallel, the plane of that surface is now parallel to the magnetic field lines, the flux through it is 0. It does not collect any of those magnetic field lines. It has 0 magnetic field lines running through it, therefore it is 0. The reason we use this formula is because it's actually a dot product here, and that means it's the magnitude of B times the magnitude of A times the sine of the angle between them. If they're parallel, this angle is 0, and therefore sine 0 is 0, and the entire flux goes down to 0. Since we can attach this loop to an axle and spin it around at some frequency, we'll say the frequency is equal to, in the first case we'll say it's 1 hertz. So it takes 1 second for this thing to go all the way around. We can graph the flux over time now. So we have time on the horizontal and flux on the vertical. It starts off in this position at t equals 0, and at 1 second it's back to that position there. So flux is 0 there, and 1 second later it's 0 again. However, as it starts moving, a quarter of a second later it's turned a quarter of its revolution. So we can put, that's 0.5, this can be 0.25, and this can be 0.75. A quarter of a second later here, if it's spinning at 1 hertz, the flux will be at a maximum. And then half a second later, half a second after the initial position, it'll be flat again like that, parallel to the magnetic field. So the flux is down to 0. And then as it keeps turning, relative to the face, we're now getting negative flux, which means the flux is effectively coming through the opposite side of the loop. So the flux goes to a negative, and then back up to 1 second. Let's now graph the flux if the frequency were 2 hertz. So now it doesn't take a full second to go all the way around, it takes half a second, because the time taken to go around is 1 on the frequency, that's 1 on 2. Can you imagine what the shape of the graph will be? Well, we have the same maximum flux, but it occurs much more quickly at 1/8 of a second. At 1/4 of a second, it's back down to 0.375, it's a minimum, and then back up like that. Whoops, that went too high. The important thing is that the maximum and minimum flux does not change. It's simply at the time it experiences it. There we go. Now the last question I'm going to look at is a question involving an electromagnet and a coil. So I'll draw the electromagnet here. We've got now the dotted lines are the lines in the background, and the solid lines are the lines in the foreground. There's our coil. It has current running in this direction, and within that coil we have, sorry, I should say solenoid, within that solenoid we have this loop, a square loop. Let's ask ourselves, is there any change in flux? Or actually, is there any flux at all in this loop here if there's current running this way through the solenoid? If there's current running in this direction through the solenoid, up at the back, down at the front, like so, if you use your right hand grip rule, you'll find there are magnetic field lines running this way through that solenoid. But notice, the magnetic field lines running through this solenoid are running parallel to the surface of that loop. So if flux is equal to B dot A, which is a dot product, and the angle between the magnetic field lines and the area is 0, then we'll get 0 flux. We'd have to turn that loop vertically, like so, to get any flux in it at all.